Today we're covering section 5-3, which will talk about Newton's third law, and then we will do an example of a application problem. Newton's third law is the equal and opposite reaction law. So if you write it out as a math equation, I guess you could say that this is the way it's written. So the force of B on C is equal and opposite to the force of C on B. And they're just giving the negative sign there as an indication of that opposite means opposite in direction. So if you're talking about two things pushing on each other, if B is pushing with a force of 10 newtons to the right, then C is pushing with a force of 10 newtons to the left. And so that's what we mean here. So that's really important because that means that there's never a case when a force comes by itself. So there are always forces in pairs. But it's important to note that those forces are on different objects, okay? So when you're standing on the floor, you are putting pressure downward on the floor, and the floor is putting a force equal and opposite, meaning equal and upward on you. So when you're drawing a free body diagram of you, then we show that force of the floor on you as like the normal force, right? And then if we were going to draw the forces on the floor, that's when we would show the force of you on the floor. So that's important. We would never put those on the same free body diagram. And then it's also true that like you cannot put a force on yourself. So sometimes you'll catch yourself doing this as you analyze a problem and you're trying to figure out, why is this thing accelerating? How is it possible that a basketball player is, jumping up and going up into the air to make a jump shot? Technically, it seems like the basketball player is the one making the effort here. Okay, so then how is it that they are accelerating up into the air if they aren't putting a force on themselves? Okay, well, that's an interaction with the floor. And so we have to think about that when we analyze problems, okay? And think about, it's a little strange, but like, what if the floor was weak? We take things for granted like that, right? But we don't play basketball on thin ice. Why not? Because we're worried that the ice wouldn't support that person. And then they would not be able to put pressure down on the floor in order for the ice, or on the ice, and then the ice wouldn't be able to put that upward force back on them that allows them to be propelled up into the air. Okay. When we talk about third law force pairs, we have to be careful because we've already drawn free body diagrams where we have an up and a down force. And so sometimes folks want to say, oh, okay, well then the force pair would be like the normal force from the table and the gravitational force, because they're equal and opposite. They are equal and opposite, but they aren't considered a third law force pair, right? Because we just said that those would never be put on the same free body diagram. So this is a silly, way out of scale diagram that shows like the fact that the force of a cantaloupe on the earth is equal and opposite to the force of the earth on the cantaloupe. So all this time we've been talking about this force of gravity, right? And that is a force that the earth is putting on every object. And it causes acceleration, right? So if you throw the cantaloupe up into the air, you will see it in free fall. And that's because of the force of gravity. So what we would normally do is call this FEC, or sorry, force of we would call this one FG, right? But it's true that the cantaloupe is exerting just as much force on the earth trying to pull it up, okay? Force of cantaloupe on earth. And people don't want to believe that, right? Because you've never seen the earth, like, well, I mean, you're standing on it, so it'd be pretty hard to perceive, but you've never felt the earth move underneath you and rise up to meet something, okay, in the middle. But that is an effect because you have a very tiny mass of the cantaloupe, right, MC, right? And then you have a very large mass of the earth. So the effects that we see in real life are really acceleration effects. So we know that Newton's second law is applying here, and we know that the acceleration of the cantaloupe is equal to the FG, right? Or in this case, Earth on cantaloupe, divided by a very small mass. Okay, so we see this. This is noticeable. This is negative 9.8. But because do we notice the acceleration of the Earth? No, because it's the same force, C on E. I guess it's opposite, right? Like technically this would be negative, right? That's down. This one would be positive, upward. But the mass of the Earth is huge. Okay, so that makes this acceleration of the Earth toward the cantaloupe very, very small. And so infinitesimally small that we're not going to ever notice it. Okay. Now, when we get to problem solving, then again, I feel like we've talked about this before, but you're going to draw the free body diagram, okay? And then here's some like little pieces of advice. So you can ask yourself, do I have enough information to solve for net force? I could, two ways to get that. Add up all the forces on the free body diagram. Or maybe I don't have them all. So do I have enough to like do F net equals mass times acceleration, which is a rewrite of Newton's second law. Okay. Another thing, do I need to find acceleration? I could find it using the old equations from chapter 2. I could use calculus if I need to, like if they give me like a velocity and I need to take first derivative. I could use, again, maybe all I need to do is do Newton's second law. Okay. Then usually the last step of a problem in this unit is to find a particular force. Like they ask me for tension, they ask me for normal force. Well, then it's like a little puzzle. Like I know some of the other forces on the diagram, and so I'm going to use the fact that I know F net and I know like FG, and then I'm like figuring out what's left. Okay, so there are no two problems that are the same, and that is sometimes challenging, but that's the trick here. Okay.